management, right, with all the limitations that it has. And I will introduce to you a little bit of an industry flavor of how all of these theories and all of these practices actually come into play on a daily basis. I also noticed that there are some practitioners as well joining us in the meeting today. So I look forward to some engagements, and hopefully we can all give more value to the students of the university. So with that, I will start. So my name is Arif, and I'm the integration project manager working with Schlumberger, currently in Saudi Arabia. I manage lump sum turnkey projects, which involves a multitude of services, multitude of service providers, and we deliver services for an external client, which is Saudi Aramco. So this morning, I will start with Wi-Fi, right? And because everyone is at home, you don't need Wi-Fi passwords and what normally is given to you in a standard facility. But in this particular one, Wi-Fi is what's in it for I. In this case, what's in it for you. So this morning, I'm going to go through with you 3 main topics. I hope it's not going to be too long. We will try to complete all of this within the next 45, 50 minutes, and then there will be some question and answer at the end. So we go through some risk and opportunity. Risk, what they are, how we identify them, and opportunity in the framework of performance, how we can boost the performance better when we drill our wells. And then I'll go through some of the drilling risks that we normally see whenever we are planning the wells, whenever we are executing these wells and delivering them to the customer. And then I will end with how we optimize performance. And I will take particular focus on drilling and flat time improvement. So a little bit about me. I started off as a field engineer back in 2003. I worked in the deserts of Mexico, in the northern part, which borders with the United States. I also, after some time, got transferred to India. At that time, we had won recently the Slim Pulse Bombay High contract. It was a low-cost MWD service for ONGC. So I spent some time there before I eventually moved to Turkmenistan. And I stayed there in Turkmenistan, taking on multiple roles as field engineer, progressing through the career, and eventually leaving the rig to do a training role and then service delivery role. So I was there in the Central Asia region, in Kazakhstan, Azerbaijan, Turkmenistan, and I kept moving around the 3 countries to deliver the services. In 2013, I moved to Myanmar to work as an operations manager. I managed the business for drilling and measurements, providing measurements while drilling and directional drilling services for the customers in Myanmar. And during the downturn in 2015-16, it was quite rough. So the company assigned me to go back home to Indonesia, where because of the downturn in the oil business, I moved to geothermal drilling. So we had an integrated geothermal project back in 2016. And instead of drilling for oil and gas, we started to drill for steam to provide the source of energy for the geothermal power plants in West Java, Indonesia. And then in 2018, I moved to Bangladesh, where it was the first integrated project that we were drilling in Bangladesh. I spent some time there until eventually I moved just last year to Saudi Arabia to provide services, drilling wells for Saudi Aramco. In the spare time, I like to do volunteer work. SPE, I enjoy a lot of these guest lectures or industry talks. with the students, and I'm always happy to give you guys a little bit of insight on how to get a job properly, you know, how to do your CVs, and how to prepare for an interview, or even just a general discussion about how the oil industry is. You can reach out to me on the social media or through emails, which I will share with you at the end of the presentation. I also do some volunteer work for the Project Management Institute in Indonesia. And when I'm not volunteering and when I'm not working, I also like to do a little bit of singing, nothing professional for a select audience. And I also do a lot of running outdoor running. Okay, so that's a little bit about me. And, you know, because of this COVID-19, and a lot of us now do everything online and through the web, I would like to know a little bit more as well about you. And so if you don't mind, kindly with your mobile devices or on your laptops, please go to this website, paulf.com/arifp025. And I have a few questions that will help me to understand the audience better. And as well, you can have also an idea of what's coming in the presentation. It's going to take just a couple of minutes. So I'm starting off with a question of asking you whether you are an employee or a student or a fresh graduate, right? So kindly go to the website and answer. I will share with you the result of the survey. Okay, so the majority of you are students, as expected. Very good. If you are just joining, welcome, and please just quickly go to this paulf.com, arifp025, just so that I know a little bit more about who is the audience. Okay, excellent. Now, the next question. If you are a student, which the majority of you are, can you please let me know which year that you are currently studying? Second year, perfect. Okay, quite a good mix and proportion of each year. Very good. Okay, so we move on to the next question. Oh, I still see people are responding. Next question is, out of these 4 topics, or these 4 words or phrases, which of the below are you familiar with? You can choose up to 3, which you think that you know what this means and you've read a little bit about them, and you have a pretty good idea of how relevant this is to our discussion today. Excellent. So the good thing that I see here is that I think some of you have had some reading, or maybe you've gone through a session regarding loss circulations and ROP, something about TVD curve, risk management. Some of you are familiar with stick charts, which we are going to touch on today. And that's very good. Okay. All right. So sorry to stay a little bit longer on this because it's important that I know your familiarity with these topics. Okay, good. What are you expecting to learn from this session? And this is a free answer, but answer in one word only. And you guys can let me know. Career, very good. I can touch on that a little bit more towards the end if you like. Wow, okay, COVID situation. Interesting. You know, it's difficult on all of us, especially in our industry also because of this global slowdown and the economic condition in each country has completely driven the demand for oil, and therefore the activities of the operators and therefore the service companies have dramatically slowed down. And I understand that maybe for some of you, it makes you a little bit worried. It gives a bit of anxiety of what you're going to do after you graduate and so on. Okay, so the major keywords here I see is I see drilling, I see risk management, I see job, knowledge, the future. I also see opportunities. Okay, very good, excellent. Thank you so much for your feedback, everyone. And I will go back now to the presentation, and then we can start. And you know, don't delete or don't close this link yet, because after this, I'm going to be asking a few more questions on the same link. Okay, so I will start with this quote, right? That if things seem under control, you are just not going fast enough. So this is a quote from Mario Andretti, a Formula One and a NASCAR racer. And basically, this is very in line with what we are going to be discussing today, because we control risk and we manage risk so that we don't get any surprises, right? So that everything is under control as much as we can. However, there will come to a point where your manager, your customer, or even yourself will question whether change is needed or not, whether we can do better or not. And this is just the nature of a human being, and also, you know, as an individual and as a collective organization. Whenever things are, you know, normal and in control, everybody wants to seek for that next step. When you are in a career, when you are a student and you are happy with your grades, or with you have your, you know, grades under control, you always want to expand your knowledge to see what else is out there. And this is exactly what we are going to do. And it's the same in drilling. When you start a project, maybe you are a little bit worried and trying to make sure everything will go well. But at some point, you're going to have to move faster, right? So as Aparajita already mentioned earlier, I'm going to have a Q&A session at the end. But please, any questions that you have regarding the slides that I'm presenting, or if something pops out in your mind that you want to ask me, please put it in the chat box and I will get back to it after we finish the presentation. Okay. And honestly, with this online environment, I have the chat box right in front of me. So I'm going to be watching it, and it will give me, you know, a sense of, you know, a happiness that I'm not talking to myself, right? So if people are responding and people are engaging, this is going to make the session even better. Okay. So risk and opportunity, right? Where is the balance? Which one do we pursue? which one is more important. So now, please go back again to this link and let me know what you think. Which one do you think is more important? Is it more important to make sure nothing goes wrong? Or is it more important to continuously push for performance and satisfaction? I always like to start with this question because it gives me a feel of your preference, right? Your risk attitude, whether you are risk averse, whether you are risk taking, or if you are in the middle. I did a similar survey last month to a group of students and some industry practitioners, and the result was similar to this, right? It was 40% saying that they would push for performance, and 60% is saying that they prefer to make sure nothing goes wrong, which is a little bit strange, especially with students, because normally, because students are young and you're dynamic, you prefer usually to push for performance, but that's okay. So let me ask the question in another way. If you were a well engineer working for a company, right, and you had some extra budget to spend, so you are drilling now and the project is ongoing, and you had some budget to improve your project, how would you spend it on technology? What kind of technology would you deploy? Would you deploy it in a technology that would give you a risk-free drilling? Or would you deploy it on a technology which would allow you to drill the wells faster, to save you money for the company and for the client, and to achieve this, breaking records and getting yourself out there and sharing your lessons learned and your achievements with the industry? Which one would you choose to spend your budget on? Very interesting. Okay. So it looks like even when I throw money to the equation, most of you, actually even more than the previous question, most of you still choose to spend it on technology which would allow you to avoid catastrophic events. Excellent. So thank you again for this, for the participation. Okay. Now that I know that most of you prefer to manage the risk and to focus your budget and time and efforts on reducing the risk, then I will go through the next part of the presentations, which is basically going to share with you on how exactly this process of risk management is taking place in the industry. So this is basically a simple phase, right, of any project. You plan the project, you execute the project, and later on you evaluate. Now, in terms of risk and opportunities, a large part of de-risking or reducing the risk of your well is done during the planning. In fact, it's one of the first things that we do. And I'll show you the kind of steps that we take in the next slides. But offset well analysis is a key risk management step, right? Knowing what has been done before and what challenges already were encountered by the previous teams before you, by the previous well engineer that you took over from, or even from a previous client which were drilling in the similar field and in the same field. By using this offset well analysis, you will be able to assess what kind of technology is applicable to overcome these problems, and even identify which is the most safe or which is the safest sequence of operations. What additional activities are you going to put in the sequence of operations to make sure that your wells will be de-risked, right? The risk will be minimum. After that comes the execution. Now, I'm not saying that in the execution there is no more risk management. Risk management is an ongoing thing. So whatever you planned during the planning phase is, should materialize during the execution. But there is also an aspect which is optimization, which is equally important for the stakeholders, whether it's your drilling manager, whether it's your customer, whether it's your field supervisor who's in the field with you. They all want performance. Safety is number one. Integrity is number one as well. But at some point, people will push you to perform. And that's why we do have to talk about performance. We cannot talk about performance without talking about risks. We also cannot keep talking about managing and mitigating risks without at some point wanting to perform, right? And the last part, which is also very important, is the evaluation. It's a smaller circle because at that point, everything is in hindsight. Everything is already done. We're just trying to capture the learnings and make sure that we improve it for the next drilling programs, for the next projects, even for the next drilling campaign. So CI that I put there is basically continuous improvement. Okay. Now, this is a bit of a lengthy slide. I'm not going to spend too much time on this, but basically these are the steps that you would take whenever you are managing risks. It starts with identification, and that involves asking for data, interviewing people, asking for the requirements. When do you need this well by? How much production are you estimating from this well? Right? What is the budget? What are the limitations, right? So all of these things is part of the risk identification based on the information, actual data that you know. And then comes the analysis, which is from all of this data that you have in your hands. You need to extract useful information. You need to extract the knowledge from that, and so that you can start weighing your options. You can start looking into what technology is available to be deployed, what best practices in the industry. You can look even into your own portfolio. If you already were a drilling engineer in a previous company or a previous drilling campaign, then you can look into your experience and see maybe you've encountered these problems before and you would like to implement some of the learnings into the project that you work on now. After you have all of these options, you prioritize the risks, then you can choose a risk response, right? A risk response, there are 4 of them, and we're going to go through each one. But basically, as you respond to risks, you also have responses to opportunities. What are you going to do with this opportunity? Are you going to pursue it? And are you going to ignore it? What are you going to do? And then, of course, once you decide on a risk response, you don't stop there, because you have to think, what if this doesn't work? Or what if it works, but it doesn't meet exactly what we are planning to achieve? And this is called contingency planning. And any well engineer, any good well engineer, any good project manager, any good students would always have contingency planning in every single decision that you decide to take, right? What if it doesn't work? Always have that in your mind. So the more prepared you are with different scenarios, then the faster you will react, and the less lost time that you will encounter whenever you run into these issues. So going forward to drilling risks, right? Managing drilling risks. And I already mentioned briefly earlier that it starts with offset well analysis. But, you know, when you are drilling a rig, when you are drilling a well, you also need to realize that you need to have a good rig, right? And here I'm illustrating that, you know, you are going to depend on the rig a lot, a lot. You won't imagine how months of careful planning, of diligent risk analysis can be completely derailed just because the rig didn't perform, just because the rig didn't have spare parts, right? Just because the rig was not up to the right specifications. So it is the most, probably one of the most important thing to be done during the planning stage. That is what's called a rig sizing, based on your reservoir, based on your drilling challenges of what you know, you choose the best rig that you can afford, and it's going to be worth it. Okay. Now, offset well analysis. Again, another busy slide. I think some of you may have already seen this before. But don't worry, I will go through it one by one. Right? So this is the output, or one of the output of an offset well analysis, which is the stick chart. It is a powerful visualization tool because it puts your well, your planned well, side by side with nearby wells that have been previously drilled. And it provides a visual information of what kind of risks were encountered in these previous wells. And you can have a quick reference of what risks to anticipate as you move forward with the planning of your well. So for example, here, right? On this stick chart, this red circle, the second well on your left, from the left, is your subject well. You are going to drill up to 7,600 feet. And these are your casing strings, your different sizes, right? And these are your offset wells. You have offset well 1, 2, 3, 4, 5, 6, 7. On each of these offset wells, there is information on when it was drilled, how long ago it was, how far it is from your subject well, and also the casing design. How many sections did it take to finish this well, right? For example, on all of the 6 offset wells, these gray bars at the bottom, these are open hole sections, which means they drilled the smallest section in the reservoir and they didn't case the hole. It is different with this one on the last well, where the last section drilled was cased off, and then there was no smaller section, or there was no section of the same size drilled on this well, which was drilled in 2012. Now, these are real data, by the way, I'm sharing you. So this is from actual wells that I've worked on before. And the most important part of the stick chart is these icons that you see in the legend here. This is a simplified version of the stick chart. The original one had maybe another 3 or 4 problems which they encountered, right? There is cellar collapse on the surface, and then there was another, there was like, for example, high dog legs was also indicated there for some of these wells with regard to wellbore stability in these tangent sections and so on. So there are more information that can be put as much as you want on this stick chart. But for the sake of simplicity, there is loss circulation, which is the yellow arrows that you see here. There is the red arrow, which is the kick. And then there is the other double-headed arrow, which is the tight hole, which means that when you were tripping in and out with your pipe, you had some restrictions and you had to work through it, quite difficult to move the pipe. And then there is a shallow gas, and then also the stuck pipe. So as you can see here, I don't know, probably you will not be able to see very clearly the numbers, but at least you should be able to see these icons. And you can see that there is one particular icon which keeps popping up, which is the yellow arrow, right? And this is the lost circulation. So what this tells us is that on this particular well, you're going to probably come into a situation where you will be drilling and suddenly you lose circulation. Okay, so, okay, I'm going to go a little bit deeper on this, so don't worry. And later on, I'm going to just zoom in on this top part, right? This is the 16-inch hole section. Okay, so I have a question here. What are the lines connecting in the neighboring wells? Very good question, very good question. So these lines, which are connecting from one well to the next, these are formation markers. So if you have been given formation markers by the client, for example, you will be entering a certain formation called, let's say, Neptune. It's estimated that you will hit Neptune at the depth of 5,000 feet. So as you drill, you learn that on this well, you hit Neptune at 5,100. On the other well, you hit it at 5,400, 5,000, 5,500. So the difference, you know, sometimes sometimes you hit it shallower, sometimes you hit it deeper. And that can help you in operationally planning, for example, your number of pipes, right? Contingency stands. So normally before the rig starts drilling, they prepare the stands to be able to reach to the next target depth. If you plan to hit the target at 5,000 and you prepare your pipes exactly to reach 5,000, then you're going to have to spend more time later on if you find out that the formation is not at 5,000. If you have to go 1,000 feet deeper, 500 feet deeper, then you're not going to have stands to work with. You're going to have to pick up your drill pipes joint by joint, and it's going to take a long time. So this will give you a bit of a heads up, right, to understand, okay, it's all around 5,000. It differs by 200, 300 feet, and you can plan for that. If you are planning for an LWD job, this will also help you to plan batteries, memory, right? Because the tools have limitation in terms of battery usage, battery consumption, as well as memory consumptions. If you are logging while drilling and you want to have that good quality data, then normally the client, the geology department, will not allow you to drill so fast because they want you to drill slow to get the high quality data. But if you have the tolerance of 5,000 feet plus minus 300, 400 feet, then you need to make sure that your memory will be able to still record even if you go beyond 5,000 feet. Right? So that's what it can be used for, these formation tops or the formation markers. Okay. So like I said, I'm going to go and zoom a little bit deeper into this. By the way, the stick chart is not the only output of the well analysis. It's only a visual tool, right? You will probably still need to do a summary of an offset well, you know, and it looks something like this. Okay, these are section summaries, which gives you a more detailed explanation of what exactly happened on that section. So for example, this one, take the 16-inch section, right? You're gonna see in this detail, because you've read through all of those 6, 7 offset wells, you've read them all, and you've summarized them. You know now, for example, why am I having all of this lost circulation? What mud weight was I using? By providing this section summary along with a stick chart, you're going to be able to know a bit more granularity, right, in the information of what was my mud weight, right, and how did they cement it? I mean, you have total circulation lost, you run the casing, but were they able to cement it? Were they able to run the casing, right? And what other problems did they have? So for those of you, right, who may not be familiar with the total loss circulation, this diagram on the left, or the picture on the left, shows you your drilling string, okay? This in the middle here is your drilling string, that's your bit, and this is your hole that you are drilling. In normal drilling, when everything is smooth, you will be pumping your mud with the required mud weight. The mud leaves your bit, and then it goes back up again as it carries out the drilling cuttings, which you have produced as you drill the hole. So the drilling fluid actually is like the life and blood of drilling. It will rotate your motor. It will provide a hydraulic jet so that you can drill easier. And more importantly, and the most important, it acts as a conveyor belt. It moves your cuttings up to the surface, right? Because if you don't move the cuttings, then you will never make any progress, because as you drill, then the bottom of your hole will be filled with the cuttings that you generate by cutting this. It's like when you drill a hole in your wall, right? The bricks or the cement that you drill through eventually comes out, because without it, you're not going to be able to put in your nails, your anchor, or your screw. So it's the same principle. However, sometimes drilling exposes you to a challenge whenever you drill, for example, fractures, right? Underground, sometimes you have layers which are heavily fractured. And the fracture sometimes is so big that whenever you drill, all of the drilling fluids, once it leaves your bit, instead of traveling back up to surface, it gets diverted. And it goes through these fractures, and it goes through these holes, right? There is also, you know, even when I was in geothermal drilling, this actually puts your mindset, or, you know, it completely skews with your mind, because you drill oil and gas for such a long time that when you drill through fractures, you see it as a problem that you need to fix. When you drill through geothermal, when you drill fractures, everybody celebrates, because that's where the steam is, and that's where the steam can be extracted from. When you drill through fractures, and sometimes the fractures, they are very big. I'm not talking about 3 feet, you know, 5 feet of a fracture in the layer. I'm talking about, you know, 30 feet. I'm talking about 50 meters of fracture, 100 feet of fractures, which is huge. And obviously, whatever you pump in the hole, it's going to just go into the fractures. It will go into the formation. You will never see anything back. Now, even though people celebrate to see these fractures, the drilling problem is still there. You still need to drill this section. And that's where, you know, a different approach needs to be taken, when you have to start drilling with air and so on, right? And all of this LCM, trying to cure the losses, this will never work, right? Because loss circulation materials normally can only be used when you have partial losses, right? If you are losing a little bit of your drilling fluid into the formation, you see that most of it or some of it is not coming back. You can try to cure these losses. You can try to seal those big pores in the formation with some flakes, some nut plug, some rice husks. Even in Indonesia, back then we were using, banana trees, the trunks of banana trees. We chop them and make it a natural LCM, because in geothermal drilling, you are not allowed to use any chemical LCMs. Everything has to be natural, because you don't want to destroy or disturb the formation. So all of these things can be learned only if you read through the end of well report. If you read through the report of the mud engineers that were on the job, if you read through the directional drillers reports to see what problems they encountered, what parameters they used to react to the situation. And by doing that, you're going to be better prepared, right? Imagine if you are going to go into a well, to drill a well, and you have all these problems, and you didn't even know that those problems existed. Imagine the confusion, imagine the money that you are going to spend on trying to fix this issue, right? So that's why offset well analysis, making a good offset well analysis is super critical. And it's one of the few things that you need to be able to pick up as a well engineer who's starting up on a job. And that's probably going to be the first things that your senior well engineers is going to assign to you, right? Look at these wells. Sometimes the customer asks you to look at the wells within the radius of 5 kilometers. Sometimes they say 10 kilometers radius, right? And sometimes they even want quantity, minimum 20 wells if it was a very busy well. Sometimes they ask you to drill, to look at wells that have been drilled only after 1995. So there are different criteria that are given by your customers or the company that you work for. So this is an example, right, of how you identify this risk. Risk identification, the first step of risk management. To summarize that red box in the 16-inch section, you might have seen a lot of lost circulation, a lot of stuck pipe being printed in bold. And then there was also one well where they had an issue running the casing. They got held up, it was restricted, they tried to push, they tried to reciprocate, it couldn't work. So they eventually set the casing 30 feet shallow, 10 meters shallow. Some companies accept this, some companies don't accept it, right? Particularly when setting the casing. If you don't cover the zones that you want to cover, the customer will just tell you that it's not acceptable. I'm not going to set the casing here. You have to pull all of this casing out again after 5,000 meters, 4,000 meters, however deep it may be. If you didn't reach the target depth, there is a big chance the customer will request you to pull out this casing, run back in again with your drilling bit, and try to clean the hole, make sure that everything is okay, and then try again with the casing. And that may cost you another 24 to 48 hours of doing this. So now that you've identified the main 3 risks on your well, lost circulation, stuck pipe, and casing running, you need to do more analysis, right? Because you're a well engineer. So you are not easily affected by catastrophic risks, right? After some time in the industry, after some times of getting used of planning to mitigate a stuck pipe, planning what to do in a lost circulation, right? But first of all, you need to know the likelihood. That's why the first line of this risk analysis is you need to know what is the likelihood, what is the probability. If you were going to go and learn to drive a car, and then somebody tells you that you shouldn't drive because there is a risk of dying, then it wouldn't be wise to, take a decision to stop or cancel learning to drive based on this potential risk. Yes, there is a potential risk. People, sometimes they get into an accident and they die. But there are also people who've driven all their lives and never had an accident before. So you need to know what is the likelihood of this happening. Because based on that, you can prioritize how much effort, how much time, and even how much money you want to spend on these risks. So for example, here, 7 out of 7 wells that you looked at, all of them had lost circulation. So we can all agree that there is probably almost 100% chance that the subject well that you are currently planning, you're going to probably run into a lost circulation situation as well, right? There was one attempt by your predecessor to cure this. They pumped LCM, they tried to cure it with cement, and it didn't work. Sometimes with this total loss, the client may force you to cement it, and then you cure the loss, but as soon as you drill through the cement again, below that cement, there is again another loss circulation zone, and you cannot be stopping every time, right? So when you talk about the cost of this risk, I'm giving an example that the money that you lose on chemicals that you pump into the hole and gets lost in the formation, and then the problems of having to slow down after you drill each stand and you have to ream, all of these things add up to around $200,000, let's say, right? This is just an example or an imaginary number. Let's say that all of the consequences of having this lost circulation cost you $200,000 in the past per well. So you look at this well that you are planning now, and you see 100% chance of lost circulation. So the cost of this risk is basically the probability of it happening, 100%, multiplied by the worst case or the worst amount of money that you are likely to spend, which is 200K. So that basically results in 200K. That's the cost of your risk, okay? Now, why is it important to quantify this risk? Why is it important? Because it will set some boundaries on how much money you are, is at your liberty to spend. If the cost of this risk is $200,000 and somebody comes knocking on your door, Schlumberger comes knocking on your door, for example, to say, sir, we have for you a solution to combat your total loss circulation, and it's going to cost you $500,000. Does it make sense? It wouldn't make sense for two reasons. First reason being, there is 100% chance of it happening, right? So whatever cost that you decide to take, you are going to spend that money. So the second reason is the number itself. If the cost of this risk is $200,000, why would you spend $500,000 to try to prevent it or to try to mitigate it? So the cost of risk is a concept that you always need to have in your mind. If you don't apply the concept of cost of risk, then you risk of becoming a person who is too conservative, right? You're not going to try things because you are too afraid of the big number. Take, for example, the stuck pipe example, the stuck pipe case, right? It happened on 5 out of 7 wells. So the probability of it happening is 70%. If somebody were to ask you, or if you were to ask somebody, what is the worst that can happen whenever you get a stuck pipe? They will answer to you, the worst thing that can happen after a stuck pipe is that you're going to lose that pipe in the hole. You're not going to be able to free it. You're going to bury it in the hole. And if the downhole string or the bottom hole assembly consists of a motor, a rotary assembly, a rotary steerable assembly, all these high technology items you leave in the hole, you're going to have to pay for that. And that's going to cost you anywhere between $1 to $2 million just for the tools alone. You still have to pay for the cement plug. You still have to think about the time you spend to sidetrack the well and to continue drilling. In my experience, sidetracking a well, minimum will cost me around $1 million That's if I don't have any high-tech items in the hole, and that's if everything goes smooth. That's going to cost me $1 million. Now, you're planning this well, and you see the risk of stuck pipe. You ask your peers, you ask your supervisors, what's the worst that can happen? They tell you, man, you're going to spend $1 million if you lose this BHA in the hole. Then you get nervous. Then you start thinking, I'm going to lose $1 million. But in fact, if you look at the offset well analysis and you read through it, yes, 5 out of 7 wells, you had stuck pipe. But all of them, in all stuck pipe instances, the team were successfully able to free the pipe. So yes, you had a stuck pipe, but you never had a lost in hole event. You never had to sidetrack. You never had to spend $1 million. And therefore, the cost of your risk, basically, is only the time that it took you to free the pipe, to jar, to pump, maybe to pump acid, right? And do all of this remediation to try to free the pipe. Eventually, you freed it. So that reduces the potential risk or the potential cost of this risk from $1 million to 7,500. 7,500 being, I'm assuming that it takes 6 hours to free the pipe. And that's only a quarter of your day rate or your spread rate, for example. Right? So in this example, in this scenario, I'm assuming that the cost of my rig is $30,000 per day. $30,000 per day. For every day that I delay my well, I have to bear the cost of $30,000. For the stuck pipe, I know from my offset analysis, I spent 6 hours to free it. So 6 hours to 30K is 7,500. That's the cost. And even that is only 70% of it happening. So the cost of this risk is even less. It's 5,300. So this is just an illustration, right, of how you should look at these risks. And you can apply this in your daily life too, by the way. Whenever you fear, right, that you are, for example, trying to get into a company, what is the chances of getting hired? And nowadays, if you go to many job portals, monster.com, they even, they have a forum there where you can see what are the chances of people getting hired, right? The proportion between people applying to a job and people actually getting hired. So you can use these simple mathematics, right, to then decide on how much time and how much money, how much effort am I going to try to get into that company, for example. And that can then lead you to decide, should I pursue a certification, which is going to cost me $400? Should I pursue a course in, basic or fundamentals of drilling engineering, which is going to cost me $1,000? So you need to be able to calculate, right, how much is the risk, and then it will help you to decide what options is the most suitable and that is worth it. Right? So the below box, managed pressure drilling, eliminating all directional work, having a competent driller, those are some of the steps, some of the solutions that you can take to counter those risks. Some of those risks, some of these solutions cost nothing. For example, not having directional work. That actually eliminates the cost of doing directional work in the 16-inch. You remove all of that so that in case you run into a stuck and lost in hole, your cost will be minimized. Let's make sure we have a competent driller. That costs nothing. That involves you sending an email to the rig company and asking him, please let me know, please share with me the CV of your driller and share with me what was the latest competency assessment result on this driller. Did he pass with flying colors? When it comes to well control, did he pass with flying colors when it comes to stuck pipe prevention certification? You can do all of these things free of charge, right? You don't have to spend anything. Okay, sometimes maybe the solutions will involve spending some money, like for example, increasing the mud weight and all of these things. Now, if you work on a lump sum contract, then these would impact your profitability, because lump sum means the client is paying you a fixed price. Drill me this well at this price. I'm not going to pay any more than this amount of money. So whatever additional technology you throw in there, whatever additional mud weight that you need to weigh up, that's going to come at your own expense. The client is not going to be paying for that. These are lump sum turnkey projects. So it's more challenging when you involve yourself in these types of projects, because you really need to decide whether it's worth it or not to spend this extra money. So, okay, casing running, I've already touched a little bit of that, but basically it's the same principle. Calculate the cost of risk. It only happened once out of the 7 wells. And even that, the client accepted it. So then you can balance whether to prioritize this risk or not. Okay, so this is basically a quick picture of how a well engineer does his risk analysis in the beginning of the well, and the risk of, and trying to de-risking the well, right? Now, I talked earlier about how you respond to risks and opportunities, okay? And by the way, thank you for the questions that you are putting in the chat box, okay? I may not answer them immediately, but I promise I'll try to get back to them at the end of the presentation. So risk and opportunity responses. In white is the options for responding to risks, and in black is the options to respond to opportunities. So obviously, avoiding a risk is always an option. This well looks like it's very risky. Let's not drill it. That's avoiding a risk to the extreme. Another extreme example is requesting the client to change the well location. If you look at this risk on the offset wells and you say, I'm not ready to take this risk and let's avoid it, you can tell the client, can you give me another well? Can you give me another location? And if they give you another location, then basically all those risks that you've looked at is going to be removed, and it's going to be a new set of risks that you have to analyze. But that's basically the concept of risk avoidance. It's completely eliminating the risk, or even up to a point where you eliminate the activity itself, right? Now, transferring the risk. Transferring the risk is what Saudi Aramco is doing to my company. They used to drill wells themselves. They used to manage the directional company. They hire the fishing company, the mud company, the cementing company, the logging company. They do all of these things themselves. They hire 17 different contractors. They manage their own rig. And at some point they realize maybe there's just too much risk and too many disciplines of engineering that maybe it's not good to take it in-house. ONGC is doing the same, right? Cairn is doing the same. In India, for example, you have LSTK contracts where you basically hire one company to do everything for you. And that's transferring a risk. Let's ask somebody else to do it so that when they run into these risks, we are covered. We don't have too much exposure. Or the exposure we have comes in a portion of the margin or the money that we pay for these companies to cover for that risk. Reducing the risk. This is what basically is the topic of this session, right? When you are a well engineer, how can you reduce this risk? What technologies are available? What operational changes can we make to reduce this risk so that we don't, come into this problem? Reducing the risk can mean two things. It can mean reducing the likelihood of it happening. It can also mean reducing the severity of it in case it happens, right? So for example, investing in a good seat belt for your car, that is an attempt at reducing the severity. You may still get into an accident, but with a good seat belt, working seat belt, you may still be safe from harm, right? You can also reduce the likelihood, reducing the frequency of your trips, combining the trips with your friends, and that will reduce the likelihood of getting into an accident. And then eventually, when all efforts have been tried, when all options have been evaluated, and there's just nothing else that you can do, then you accept this risk. When you look at the risk of lost circulation, for example, right, in the previous slide, what risk option do you think the well engineer took when it comes to lost circulation? He accepted, right? 7 out of 7 it happened. 6 out of 6 probably happened as well prior to this last one. But they continued to drill, which means, you know, they have accepted the risk and then lived with it, lived with the cost and absorbed that cost. Okay? So these are, and in black, ignoring, sharing the benefits, enhancing the likelihood to achieve this opportunity is basically the same, but in the realm of opportunity, right? We always have to think what we can do for each of these opportunities. Okay, so that's basically the gist of risk management whenever you are planning your well or even executing your well, right? You look at the identification and then you analyze it and then you quantify it. You put percentage into the likelihood. You put a dollar value to the cost, and then you come with this eventual number of how bad this is, right? How bad is this risk? What is the cost? What is the classification of this risk? Is it a light? Is it a major? Is it a catastrophic risk? Then you can prioritize these risks and you can start allocating resources on how to tackle them. So now that you already have a good control of the risk, as we've discussed earlier, sooner or later, people are going to want you to maximize your performance. And here we talk about ROP, rate of penetration, and we talk about flat time, which is basically everything else we do when we are not drilling. And I'll show you some examples later on how flat time is actually equally as important as ROP. And we do this by looking at time versus depth curve, TVD curve, which visualizes, right, how you do against the plan. And sometimes your TVD curve for a well gets benchmarked against another well, right, to see how you fare against the other wells. And if you are managing a project where you have multiple rigs drilling multiple wells, then you can even create some kind of competition between one team and the next, one rig and the next, to see how fast they go and how fast or how good they are at maximizing ROP and minimizing flat time. Okay, so this is what a time versus depth looks like. Okay, it impacts well delivery and it's very important for your customer. For every day that you delay or for every day that you are behind the set plan, then there is a dollar value lost for your customer, not just for you. Because these wells would have been producing and they could have lifted the oil or they could have lifted the gas and sold it to the customers. And it would have resulted in revenue and profits and so on. So every day you delay due to your inefficiency, it impacts the client directly. So what information is there on this time versus depth? Obviously, your whole section is there. It gives you an idea of, so these dotted lines would be equivalent to the whole sections that you are drilling. So here you have 1, 2, 3, 4, 5. You have 5 whole sections for this well. And then it seems like after reaching this depth, you go back up again and you drill again the same whole section. So when you see this on a plan, right, this is blue, it means it's plan. When you see this on a plan, this basically indicates a dual lateral well. It means you go and complete, you reach the reservoir, and then you set a whipstock, and then you drill through the casing, and then you do one more lateral. Then you're going to complete the well with 2 laterals, basically, right? What else does this tell you? It tells you also the time, the expected time. You should be completing your first lateral within 30 days. That's what it's saying. And you should be completing this well within around 55 days. That's your deadline. Anything you go beyond that, you create loss for yourself and for the customer. So that's your plan. And then as you drill, you're going to start tracking, and you're going to start plotting a red line in the same fashion, right? And it will show you how you do against your plan, right? When you make this plan, and it's you, right? You're going to be a well engineer. You graduate, some of you will become a well engineer. And when you build these plans, most of you will factor in some risk, some delays, 10% delays, 15% delays, and then you're going to try to build it into the plan. And that will give you an opportunity for improvement, but also a cushion for you in case the risks actually happen, right? So that's your improvement margin, basically. The cushion that you build into your plan will act as your areas of improvement opportunity. So rate of penetration. I want to stress something here, right? You hear it a lot that people have to maximize the ROP, drill as fast as possible. But in reality, it is not about maximizing. It is about optimizing. And what does optimizing mean? It means maximizing your ROP, but without sacrificing other things. There is a paper from the early 2000s by some colleagues of mine, right? It was a Chevron project in Thailand. And they established some performance qualifiers which affects or which limits the ROP, right? Which means that you cannot just go full blast on the ROP. Because when you do that, you may sacrifice your directional control. When you are drilling. Hello, everyone. Can you hear me? It seems like I've lost the connection.
Yes, sir. We can hear you now.
Okay. How long did you lose me for?
5 seconds, not more.
Okay. All right. Can you see my screen again now?
Yes, sir. Yes, sir.
Just give me one moment here. Okay. So sorry about that. Where was I? Okay. So there are limiting factors on ROP. There is directional work, vibrations. In Saudi, not long ago, we were drilling a well, and we were pushing the ROP so much that it created a lot of vibration. And what happened was the vibration was transmitted all the way up to the rig, to the mast. Even the drillers could feel that the rig floor was shaking. Nevertheless, they continued, they pushed. It was almost to TD, so they decided, let's just bear with it. And what happened was because of this vibration, some of the screws became loose in one of the equipment. And not long after that, the top drive, which is on the rig floor and driving the system, and this top drive is very heavy, right? It's in the range of I would say maybe almost 1 ton or maybe more, right? It fell to the rig floor and it just damaged everything. And the rig eventually stopped for more than 2 weeks because they had to replace the top drive. They had to do another integrity check on the lines, on the drawworks lines, on the mast, on the rig floor itself. And then the string eventually obviously got damaged because it hit the bottom. So it was a real catastrophe. And for what? For trying to save an extra hour on drilling? For trying to break a record? You know, all of these things are good, but it should not be at the expense of something bigger. So that's why ROP, yes, we have to maximize it, but we have to be careful that we don't sacrifice other things. Maximizing ROP, there's many things involved, but if I can summarize it, it's largely impacted by your bit selection. Many companies, they invent a different cutting mechanism. Many companies invent a different even materials, and you know, they continuously improve the hardness, the angle of the strike to the formation, which will improve your ROP. You also have the drive system, right? Obviously, rotating is always the preferred method of drilling. When you rotate, you get good hole cleaning all the way to the surface, and you get more cutting action when you are rotating the whole string. So, and you know, this increased RPM, if you are using a PDC bit, it will give more effective cutting action, and you will have an increased ROP. Having an optimum parameter as well contributes to minimizing shocks, because if you see a lot of vibration, whether it's downhole or whether it's on surface, basically the energy, instead of it going to the bit to remove the formation, then that energy is being used to shake the drill string, to shake the mast. So there is an energy loss elsewhere other than drilling, and that's going to impact your ROP, right? And the main parameters here is basically your flow rate, your weight on bit, and your rotation per minute, the rotation of your drill string. Now, this is something for you to explore, right? I put a red box here of a monitor which says AI, artificial intelligence. Operating parameters is one of the first area that many companies, including Schlumberger, try to use artificial intelligence. We try to let the machine tell us what is the best and optimum parameter. When was that? 2009, when I was still in the field. So 11 years ago, we used artificial intelligence in advisory mode. Advisory mode means that we tell the machine real time what parameters we are using, and the machine gives us feedback in the monitor. Please increase the weight on bit to this much. Please increase the RPM. Please reduce the RPM. So it was giving us advice on how to manage the parameters. Now, after 10 years, even earlier than this actually, the artificial intelligence, we took it to a different level. It's no longer advisory mode. We can even connect this software directly to the rig equipment so that it could manage directly the flow rate, the weight on bit, and the RPM. So it will find, based on the feedback real time, it will find the best parameters to use, and it's going to modify the parameter by itself. So these green coronavirus icons here, these are the things that can disrupt your attempts at maximizing ROP. the experience of your directional drillers, the experience of your drillers, having a tool failure, whether it's a straightforward malfunction or whether it's because you've pushed the tools beyond its specification. It will basically diminish whatever you are trying to gain from these efforts. So it's very important that you stay within your operating parameters. It's very important you try to find that sweet spot to maximize the ROP by adjusting these parameters. So respect the spec, respect the specification. Oftentimes when you are drilling, you always run into these arguments and disputes. Somebody will tell you to push, put more weight on bit. Somebody will say, don't, this is going to damage my tools. Somebody will say, there is a risk that we will not catch with the trajectory. So it's always a balance that you as a well engineer later on have to consider to try and, to try and find a win-win for each of these limiting parameters. When it comes to flat time, right, there are high frequency events which occurs on a daily basis and very frequent, like tripping, connection practices, right? These are high frequency events. There is also events that are low frequency, like BOP testing, which occurs every 21 days. There is casing and liner running, which is done only after you finish drilling. But as you can see here, out of all these four, there is a contrasting difference, right, between these four with the previous three, which I just showed you earlier when it comes to ROP. And the difference is human factor. When it comes to maximizing ROP, a lot of the things are affected by your bit, your equipment, basically, your bit, your drive system, and even the parameters now is impacted by how good your rig is and how good your artificial intelligence that you are deploying and all of that. When it comes to flat time, it's almost 100% human. Running in the pipe, in and out, and making connections. The majority of the rigs worldwide, they still rely on the skill of the roughnecks, of the driller, of the assistant drillers who's managing the activity. And many of these flat time inefficiency are a result of a lack of focus. For example, because it's a high frequency event, people tend to take it for granted. People tend to think like it's a routine and then they just underestimate it. And the result of that can be catastrophic. Making a connection, for example, because Roughneck was not diligent to clean his workspace, he accidentally kicks a spanner, which is lying on the rig floor, and it falls into the hole. Then that will create problems, right? Making a connection, staying in the line of fire, getting hit by a rig tongue, which will suspend the operation, and even worse, it may even hurt somebody, right? And all of these things will cause delays. All of them will cause delays. Whenever you have an incident, there's nothing worse. There is nothing worse than getting delayed because of an incident. Because not only it affects your time, it affects morale. I've been on a rig where we had an employee pass away because of a rig accident, and it destroys the morale. When I was in Myanmar, I came to a rig where not long before I came, there was a person who fell overboard and drowned. He slipped basically when he was walking from his accommodation to the rig floor. There is a bridge that's called the Widowmaker. It's dangerous, that's why it's called that. And he slipped, nobody knew, he fell, he drowned, and then he died. And was it related to drilling? No. Was it, somebody who is being struck by a drilling activity? Also no. But it impacted the rig very badly, right? It delayed everything, and it also ruined the morale of the people because everyone was feeling sad because of this. So human factor is a big, major part of minimizing flood time. High frequency events is like when you do things regularly. You tend to go slow in the beginning, but later on, you're going to do it faster and faster with time. And companies should try to continue exploiting this area. And this brings me basically to the story of the Project Orcon. Couple of you, I think, have heard of this before, but this is basically the foundation of behavioral engineering. In 1944, there was a behavioral engineer, there is a human and animal behavior professor from Harvard University called B.F. Skinner. He studied animals for many years, right? And what he found was that you can train animals quicker by giving them incentive, right? Food or whatever it is, right? When the animal does something you want, you incentivize them, and then they will do what they want you to. They will do what you want them to do. So in this experiment, he built a pigeon-guided missile, a concept, right? So what happens is, because he already trained these pigeons, so he put a screen in his lab with a dot or a square or any object on a blank screen, right? And this object would move around, and Skinner would incentivize the pigeon by giving him food every time he successfully pecked the moving target. So they would place an electrode on his beak, and you can Google this or YouTube this, it's there, and it's very interesting. So every time the beak would peck correctly, it will send a signal to the computer indicating then how accurate he was. And it was almost 100%. And you won't imagine, because these pigeons, the brains react and move 3 times faster than a human brain does, right? So whenever it sees these moving targets, it's going to keep pecking as it moves. And then after 5 or 10 successful pecks, he will get food. So he used this principle by putting a pigeon on the missile head. And the missile head has 3 circles or 3 windows, as you can see there. So the idea basically is, as the missile moves towards, let's say, a battleship, this pigeon would see that battleship through the 3 windows, and it would peck the reflection of that battleship. And the signal will then be extrapolated, triangulated, so that the missile can guide itself and bring itself back to the correct trajectory and eventually hit the target. Unfortunately, the pigeon would probably die as they hit the target, but it's a fascinating thing, you know, when we can try to engineer the behavior of animals. And humans are animals too, right? And Schlumberger, for example, we embarked on this behavior engineering methodology back in 2016. So it's been on for 4 years now, and it works. And what it is basically repetitive actions, giving feedback. And the feedback is obviously not food, but it's encouragement, good job, or even a constructive feedback. Next time, do this, immediately, done on the spot. And when we do this, we give the feedback every day, every shift, then people start improving. And then we start standardizing the way people do things. There was an experiment done as well, folding paper aeroplanes. I'm sure most of you, if not all of you, have folded paper aeroplanes when you were little. We gathered a group of people, of 20 people in the room, and asked them to make a paper aeroplane. And then we asked them, after they get the paper aeroplanes ready, we asked them to throw this paper aeroplane to a certain target. And the result was, you know, one was going this way, another one nosedived and fell to the ground. Some of them hit the target, but it was very inconsistent. So then in the same experiment, after that, the instructor showed a step-by-step tutorial on how to fold the best paper aeroplane. And everybody folded the same way. And then they produced very similar looking paper aeroplanes. And when they threw the paper aeroplanes at the target, more than 80% of the paper aeroplanes actually hit the target or fell within the zone that we were asked to throw them in. So standardization of repeated tasks and giving them guidance of how to do things and making it consistent and the same on every connection, on every well, on every rig, that's the key to minimizing flat time. Because these are all basically repetitive actions, right? High frequency items. People are going to get accustomed to it. And when you shape them in a certain direction, then you're going to get progress. So when it comes to flat time, when it comes to performance, you need to hire and build the best team because people make a difference. And I don't know how many of you are familiar with this team here. This is the best drilling team in the world. And it is a team led by Bruce Willis, who went from an offshore rig in the Gulf of Mexico. He flew to outer space to drill a meteorite which was going to hit Earth. Imagine that. Must have been one hell of a team, right? So this is from a movie called Armageddon back in 1998, and it was a very popular movie. I think it still is until now for the people in the drilling industry. If you haven't seen it, check it out. So moving to the final phase of the cycle, right, which is evaluation. So as I mentioned earlier, as you drill the well, you're going to track the progress of your well with a red line and a green line. The red line meaning that's the actual time, the execution, and the green line is an imaginary line or a wishful thinking line, if you can call it that, right? It's basically, had I not had these problems or these delays, how would I be doing against the plan? So basically the green line is your clean time or your performance time, removing all of the non-productive time, removing all of your inefficiencies. That's how you would have performed against the line, the planned line. So on curve A, you can see that they had some issues in the shallow section here. They drilled up to the 16-inch section, to 12.25-inch section, sorry. And then something happened here, which resulted them to stay flat for a long time. And instead of continuing down, they went back up, which means this is a sidetrack. Something bad happened on this section, which resulted in them having to sidetrack and re-drill this well. And then they tried to recover. They drilled quite well. As you can see here, the clean time, the slope of the green line is actually steeper than the planned line, which means we were doing much better than the line. And then the progress continued. And then this again is a duolateral. So now they eventually got past this duolateral and they are now in the stage of completing the well. On B, so this is an example of how flat time and all of these drilling problems can affect you. So what happened here? Let's see the loss, right? This well was supposed to complete in 55 days, and it will be completed in around 70 days now. The next is a good example of a well which was delivered almost on time, right? You can see the dynamics of it, right? They did very well when it comes to drilling. It was always steeper than the plan, except for this one, this 8.5-inch section. Here, they were drilling slower for a reason. I think it was because of the trajectory. There is a lot of directional work to be done here. So they had to do more directional work than they had anticipated. That's why it was slower. And they lost whatever they managed to save. They unfortunately lost it during this time, but then they recovered it back during the flat time of the completion, and they managed to close it very, very close to the time. Here in C, you can see a prime example of good operations during drilling and during flat time. This is a current well, by the way. This is one of the wells that we are drilling right now. This is taken from a morning report from yesterday. And they've done quite well during the flat time, you can see here. They've done very well during drilling. So let's hope that it will continue. And if this is kept at this pace, as you can see here, there is already around a 5-day saving to be had. So if we take that previous example of $30,000 per day, 5 days of saving is equivalent to around $150,000 of benefit, right? That can be enjoyed by yourself, by the customer. Now, all of these things, right, is not extreme, right? I'll show you a well which I was previously involved, which was a disaster well. And this will show you how bad flat time can be. This is what happens when the organization cares only about drilling. This is what happens when the organization hires the best drillers, but not the best supply chain people, not the best HSE people, right? Not the best logistics specialists. And this is what happens. This well is supposed to be drilled in 55 days. It's a simple exploration well. And the scenario here is that it's a dry hole TVD, dry hole time versus depth. We assume that we are not going to find anything. So we don't know what will happen after we find, for example, a reservoir here. Maybe they're going to do some testing and all of that, so we don't include it. But the drilling alone should have lasted 55 days, including the basic completions, or the abandonment, sorry, not completions, because it's exploration. Here, look at this. Just visually, right? Was there any problems in drilling? Yes, slightly here. And what was that problem? Waiting on diesel. Was it a formation issue? No. Was it a tool failure? No. It was because the rig had run out of diesel. They stopped for almost a day. Look at the next section. Was there any problem in drilling? Again, no. We in fact even avoided a wiper trip here, where we were supposed to stop for a little bit and clean the hole before continuing drilling. We avoided that and we continued drilling successfully. Perfect. Next section. We had some issues. We had some challenging pull out of hole after reaching the coring depth. And then we had some changes in the coring program, which required us to core a little bit more. So that was the reason why we had these breaks during the drilling. But overall, you would agree that there was no issue in drilling. All the issues happened during the flat time. Look at this. This is almost a 3 weeks delay alone. Only after drilling the first section, the rig spent 3 weeks waiting on the wellhead engineer, waiting on the welding electrodes, waiting on mud pumps, spares, and many other things, right? And this is because we were operating in a remote location, and we knew that there were logistical changes. And thank God this was not a lump sum turnkey project. So Schlumberger, I was managing this project, but on a time and material basis. And all the logistics, all the supply chain, safety and all of that was not within my scope. My scope of work was to manage the drilling part of it. They hired us to manage the drilling, which we did well, almost with 0 non-productive time. But the inefficiencies that they had, that the client had, right, in the organization, severely impacted drilling. So I know that maybe when you are a student, you tend to focus more on the technical aspect of things, but believe me, when it comes to the real practice, industry practice, there is a lot of non-technical things at play, and they tend to impact you more than the technical side of things. So logistics, waiting for this, waiting for that, and having an accident. All of these things are severely impacting your performance, whether it's financial performance or even your reputation, right? This well, by the way, after seeing this and all the losses, they eventually abandoned the project, and it was not a good story. Right? It was a good story in terms of drilling, but overall as a project, it was not a good story. So flat time can be equally important, if not more important, depending on the organization you are, and you need to also start paying attention to these things. And if you are tired of looking into, like, for example, you are preparing for your thesis or your final project, right, for graduation, look into flat time optimization as well and see that what kind of research is being done on this particular subject. Look at behavioral engineering, right? Look at standardization of processes. There are so many things that is being done also in the flat time optimization area, because as you can see, it can be equally detrimental to the project. Okay, so that basically concludes the whole explanation. So I hope when somebody now asks you, which one is more important? Is it risk management? Is it optimizing, or is it minimizing? Whether it's ROP or flat time? I think the answer would be, it depends, right? It depends. It depends on the organization you're in. It depends on the state of the project. If you are already spending so much money due to accidents, then probably risk management should be your top priority. If you've been running a project risk-free for the last 2 years, there is no any more surprises, you know your wells in and out, then probably optimizing ROP is your most important thing to be allocating your time and resources. If you have the best drilling technologies, you're using the best service companies, and you manage your risk very well, but the issue is your rig contractor. You have inexperienced crew who is always changing, people are resigning, people are getting changed, then maybe you should look at minimizing flat time as your top priority. Maybe you should look at behavioral engineering. Maybe you should look at standardization of work processes, right? So the answer is, it depends on where you are and what is the priority of that project based on your current performance. So what have we talked about so far, right? So we've gone through the differences of risk and opportunity and how we respond to them. We've talked about the cycle of managing risk, identifying, analyzing it, and eventually choosing a solution that can be implemented. And then we've also looked at optimizing the ROP during drilling and also minimizing the flat time. So this concludes what I have to share with you today. It's a little bit longer than I had expected, but I hope that you can get some value from this morning's session. So I will give it back now to Parajita to host the Q&A session. And I'll take some time to look at comments that maybe I have missed.
Okay, thank you very much, sir. It was a practical and engaging session with the mix of your industry experience. So before we start the Q&A section, I would like to inform all the participants that the feedback forms and the quiz forms will be provided to you in the chat box, and everyone is requested to fill the feedback forms, as it will signify your presence in the session and help us while giving out the certificates. And also we will send the forms to the registered mail. So yeah, the session is open to the house. Everyone can write their queries in the chat box so that sir can choose the session related queries so that we can wind up on time. So I think we have some questions, sir.
If you want to talk to me directly also, you feel free to turn on your video or your microphone and we can have a better engagement. I'm also okay with that, okay? I will start with a question from Palash. What is the role of machine learning and artificial intelligence in offset well analysis, and is it being currently used anywhere? Yes, it is being used. It is being implemented in its early stage. I don't know too much details about other companies, but in Schlumberger, we are integrating the entire well engineering cycle, right? From planning, design, planning, execution, evaluation. We are converting all of this process into the cloud. So instead of every engineer having their own software, and then you have another cementing engineer who is doing a simulation on his own software, you have directional engineers who are planning their trajectories and doing the torque and drag simulations on their own software. We are converting into a big software. There is two. That one is called Drill Plan, another one is called Drill Ops. And Drill Plan is basically for the engineering side of things, to plan for all of these things where multiple roles of people can enter and input their simulations and their engineering work. And the operation side of things is going to record and complement the result against the objectives. Now, where does the AI come into play? So in the design phase for the offset well analysis, it's starting only from the database, right? So we look at the historical parameters based on the trajectory. We looked at the historical properties of cement, whether it's gas migration additives in there, added or not, and so on. So all of these things, it's going to be processed, this whole thing with the big data, right? That's what we are moving towards, that everything is in the cloud. It's going to be accessible and connected to all the many databases and best practices that's done, even outside of the company, outside of the client organization. So Schlumberger, we have our own knowledge database, right? Where we have best practices, lessons learned, case histories. Those will also be pulled in so that it can be linked. So if you see a risk on your upcoming well regarding this criteria, then the machine, the software will immediately give you the case histories of where this has happened before. So for example, in one of the wells that I showed you, if you remember, there was a jar twist off, right? And now as an engineer, you scratch your head, why did this jar twist off? Is it because of metallurgy? Is it because of drilling parameters, harsh drilling parameters? And, or is it because of something else? Is it because of a sudden impact? But you want to know, right? You want to know what causes this. Then you look at that event, and then the machine will be able to tell you, this is the list of things that have happened before. And if the jar company is Schlumberger, the software will tell you even the success rate of these jars. When was the last jar failure that we had? Was it the twist off? What was the mechanism of the failure? And so on. So yes, it's being implemented, and it's a very good area to explore. And our industry is such a dinosaur industry, right? It's such an old industry, and you guys, you are growing up with all of this technology available in front of you. You are exposed to mobile devices at such an early age, and you need to take advantage of this and see how this can be optimized, or this can be used to optimize your work, right? And so yes, it definitely is a good area to explore and to look into if you are interested in artificial intelligence. Next question. Also is, what is the difference between flat time as an NPT? Very good question. So flat time, like I said, is everything that we do when we are not drilling. And NPT is basically non-productive time. So NPT normally results from failures, something that is not in the plan, right? You never plan to have a jar twist off. You never plan to have a kick, right? So all of these things are or tool failures. You don't plan for them either. So these are non-productive time. It's non-productive because you are not making any progress, and this activity, whatever you are doing now, was not in the plan. Flat time is different in a sense that the activity that you are doing was actually planned. It's a planned flat time. You have to run your casing. You know, you're not making any progress on your depth, but you have to run your casing. You have to test your BOP, and you need to plan this into your well time. So when you are not drilling, that's your flat time, and it's a planned flat time. Sometimes you take longer than your planned time. When you take longer than your planned time, this is not NPT. This is still productive time, but it falls under what's called excess time, right? Invisible lost time, let's say, right? So at the end of the well, for example, it's very easy to quantify how much time was lost for an NPT. If you had a tool failure or a bit failure and you trip to the surface, you change, you run back in the hole, that's 24 hours, 1 day. So if somebody asks you, what was your NPT? 1 day. How long did it take you to complete the well? 1 month, 30 days. So what was the time excluding the NPT or the clean time? You can say 29 days, right? Straightforward. But the problem is sometimes it's not straightforward. Sometimes you look at the plan, it's asking you to deliver a well in 30 days, but your actual time is 40 days. So there is 10 days of delay. But when you look at your NPT, there was only 4 days of NPT. So what is this 6 days? It's not NPT. It's also not drilling. So what, you know, or maybe it is drilling, but longer than it took, than you originally planned, right? So that's invisible lost time. Invisible lost time is basically all your planned time, whether it's drilling or flat time, but you took longer than your plan. So that's the difference. I hope that clarifies it, okay? Another question, thank you, Anil, for your question. The next question is from Kundil. What are to be considered in top priorities while managing the risk? So as I had earlier explained, right, risk analysis includes quantifying them. And after you finish quantifying it, you can prioritize them. So how do you prioritize it? There is many ways, right? And it's different from one organization to the next, from one project to the next, and even from one person to the next. So risk of safety is usually the first one. Well control, also that's a non-tolerable risk. And then you have, for example, for drilling, hitting the target is also something that you don't want to compromise, right? So whatever initiative that you have after that, you must not sacrifice those things. Now, how do you prioritize it? You prioritize the risk based on the residual risk, right? So you have a potential risk of, let's say, losing this BHA in the hole, losing the string in the hole. And then you list the things that can be done to prevent this. Now, you ask yourself, if I implement all of these things, would the risk still be here or would it be reduced? If it's reduced after you implement these things, then the priority becomes less during the execution. Then you can focus on other things, right? And that's how you prioritize it. You prioritize it based on the severity of it and the likelihood of it in the beginning, and then you compare it with the likelihood and the severity of it after you have implemented those things that you plan to implement. If it's still very high, then you still need to pay attention to that. And sometimes if the risk is high and then you implement all of these things and it's still high, the risk is still high, then you will probably need like an approval from somebody higher than you. You would need to raise the flag and say, sir or ma'am, if I already implemented this, the risk is still there. How do you want me to proceed? Do we continue or not? Right. Okay. Thank you, Kundil, for the question. Now, another question is from Irfan. Does Six Sigma have any relevance in oil rig in terms of managing risks? So Six Sigma basically is, for those who are not familiar, right? It's an approach being done by the airline industry in the beginning to try to reduce the deviation. So when you have a bunch of people doing something, or when you're producing a product of many quantities, you want to try to minimize the variance or the quality, the variance in quality. So that when somebody, for example, picks up one pen out of the 1 million pen that's in front of me, and then I pick another one, the quality should be the same. It shouldn't be that this is much better pen than this one coming from the same batch. So yes, the oil industry looked at the Six Sigma for many years now. When I was still a field engineer, we looked at lean initiatives, we looked at Six Sigma initiatives, and we tried to reduce the deviation in terms of tool failures, for example. And what we did was we introduced what's called standard work processes. And these are checklists. Believe it or not, back then, we didn't have checklists. We just had like a manual, and we relied on people to follow the manual, but it was not done systematically. So some technicians would, for example, change the O-ring of a component. And some other engineers will say, maybe this doesn't need to be changed now, I'll change it next time. And then you have a failure on that. So what we did, we looked at all of the maintenance processes, we standardized them, we put them into a checklist, we gave very rigid criteria. So for the O-ring, for example, how many hours has it been run? If it's more than 200 hours, replace it. Same with the jar. How many pumping hours has it gone through? What do we do after 200 hours? What do we do after 700 hours? So every single service level is triggered by a certain specific criteria. And that is basically largely driven by the Six Sigma principle, right? Or the lean principle of trying to eliminate waste and all of that. That goes all hand in hand to try and produce a product within a set given timeline. Because sometimes if you go to a workshop we have a center called Center for Reliability and Excellence, CRE. If you go there, it will take maybe 8 hours to prepare a downhole motor. If you go to another workshop in a different country, it will take them sometimes a day to prepare a motor. And that's because there's a lot of waste when they prepare this. So we looked into that as well to try and standardize the delivery time. If the client asks me, please mobilize a motor, then as a field manager, I should be able to say, okay, I need 8 hours or I need 10 hours. And I should be able to follow on that promise, right? And that's where Six Sigma has been implemented. In terms of managing risks, so that's, it's there, right? I mean, it's embedded. We try to reduce the variance, basically, by implementing whether it's checklist, procedures, or lessons learned. And that's how we manage the risk and reduce the variance to an acceptable level. Won't the increment in mud weight lead to increasing swabbing effect and increase the gasket percentage while mitigating caving problems? Well, actually, they are the opposite, right? If you talk about swabbing effect, okay. So basically, we have to separate this question into two, right? One is the wellbore stability issue for the caving. If you have cavings, it is more than likely that you don't have enough hydrostatic in your hole, right? Or if the caving is is of clay, and it's because of inhibition. So the way to combat wellbore stability is you have to increase the mud weight. And normally there is a mud weight window that we are allowed to play with so that we don't get these cavings. Because when you have cavings, you're going to have issues with drilling because the hole is falling in on you. And during a static time, when you are making connection, for example, you're going to spend around 8 to 15 minutes stationary. And if the wall of the well is falling on you, the moment you start to continue drilling again, you may be packed off and you cannot move the string. So you have to increase the mud weight. Now, when you have a higher mud weight in the hole, obviously you're not going to get any gas cut because there will not be any influx of fluids into the well. When you talk about swabbing, this is a drilling practice or an operational practice, right? Where the driller, normally they move the string too fast and you create like a swab effect, like on a syringe where you pull the syringe and then you can suck the fluid, which is a result of this sucking mechanism. So the same when you are drilling and you are tripping the pipe too fast, you may swab the formation. And if you are in a formation which is water-bearing or any fluid-bearing formation, you may get this swabbing effect. But it doesn't mean that to avoid swabbing effect, then you don't increase the mud weight. What you have to do is treat it separately. The mud weight is required to maintain a certain hydrostatic to keep your wellbore stable. But operationally, you need to inform the driller and you need to instruct the driller that to avoid swabbing, or that you are in a reservoir which is water-bearing potentially, and there may be swabbing effect. So he needs to be careful when he moves the pipe. So for example, he needs to ensure that there is a circulation there right before moving the pipe. And when he moves the pipe, he needs to make sure that it's not too fast. And you cannot say to a driller, too fast. You need to give him a speed, right? You need to give him how many feet per hour of speed that he needs to maintain. So that will prevent such complications. Okay? From Rakesh, is downhole tool failure considered flat time? No. Downhole failure is considered non-productive time, an NPT. And normally people get penalized for it. When you have a flat time, when you spend more time drilling, for example, you expect to drill this section within 1 day, but you end up spending 2 days because the formation was hard or because of trajectory control, nobody will penalize you for this. But it does affect your KPI, right? It does affect your time versus depth. When you're supposed to finish a BOP test within 7 hours and you spend 15 hours doing it, nobody will penalize you. You cannot penalize the rig for taking an excess time. But if a tool fails, if a mud pump fails, then the company responsible for that service will be penalized financially, right? So for example, if I hire a rig now and one of their equipment breaks down and it costs me half a day, then I'm going to deduct $15,000 from the day rate, from their 30,000 day rate, for example. Or I can penalize them with a certain percentage, depends on the contract. But usually downhole tool failure or any tool failure will have financial implications. Okay. Is there any other question? Because I see that we've come to the end of the question on the chat, at least.
Yes, sir, you have covered all the questions in the chat box. If someone have any questions, then you can unmute yourself and interact.
Okay, so there is another one here just now coming in from Rakesh also. But before that, guys, if you don't mind, if you still have that POLF link open, I've activated one survey where you can give me your feedback about me, or if you have any direct question that you are shy to ask or you want to ask me directly, you can feel free to use this link and answer the feedback there. Okay, it's on the same link that I gave to you earlier. Okay, so now coming to the other question, right? Little bit about reservoir mapping during drilling. That's a very big topic to be covered in a Q&A. But, you know, we've come a long way in terms of reservoir mapping, right? In fact, the segment that I used to work for, Drilling and Measurements, we have a range of well drilling services, right? To map the reservoir and to geosteer, and to ensure that you are landing your reservoir and you are drilling and staying within your reservoir. And it's come a long way from looking laterally, like, so if you have if this is your string, right, and you have an LWD string here, the LWD will allow you to see the formation above and below you, right? So that will give you some guidance to be able to stay within your reservoir. But this is only good, this is very useful, particularly after you land and you are already in a horizontal section, right? And you are navigating through this reservoir. We have now also invented a tool which allows us to see ahead of the bit, so that even when you are drilling, you will be able to see a little bit, have a sense of what is actually in front of you. And this is very useful, both for the petrophysicists, for the geologists, to allow us to ensure that we hit the target as we planned, and also for the drillers, right? For the people in the operations side of things, they will be able to react accordingly based on what they are about to see. So that's a good area. If your interest is on the side of the reservoir, then that's also a very good area to explore. And there is so many technical domains even within that reservoir mapping alone. There's a drilling aspect to it, and there is also the reservoir or the production aspect to it. Okay. Any other questions?
I think that's all, sir.